Okay, let's look at the current division. Here we have the n elements connected in parallel, and the current I and all these impedances are given. We are trying to find the I sub k through the kth element. And here, as we did for the voltage division, we can write the element constraint first. So the element constraint for the kth element we have is I sub k. Instead of using impedance, we use admittance. We'll see why very quickly, and we'll see. So in this case, we have y sub k times v sub k, and we also, based on the key VL, we also know v sub k is equal v, right? And for based on the equivalent admittance, and we have I is equal YEQ times V, right? So, or in this case, we have V is equal I over YEQ. So if we call this the first equation, this one the second equation, and this one the third, and so we can plug the second and the third equation into the first one, and what do we get? We will get I sub k is equal to y sub k times v. V is equal I over. So we have y sub k times v. We replace the v by the third equation, which is I over YEQ, right? So therefore, we can write the YK over YEQ. We know YEQ is just the sum of all the admittances, Y2 plus Y sub n, right, times the total current. So this is the current division. And if you use the impedance, you have a lot of 1-overs, right? So in that case, if you replace y sub k by 1 over z sub k, you can replace y sub 1 by 1 over z sub 1, and so on and so forth. So you can write that equation also. If we write it out, that would like something like this. So that would be equal 1 over zk divided by 1 over z1 plus 1 over z2 plus plus 1 over zn times I. So if you use the impedance, a little bit more complicated, right? Using admittance is more compact. Okay, let's look at an example of the parallel connection. So here we have the parallel connection RLC. All these values are given. So RLC value given, and we have these the current sinusoidal current also given, but pay attention to here we're giving a sine function again, and we're trying to find the equivalent admittance seen by this current source. And for the steady state, and admittance actually is not that difficult to find. So the admittance, we can find y sub r is equal 1 over r, right? So you have numbers. So that's actually, this one is easy, 1 over 2 Siemens, and y sub L is equal 1 over j omega L, 1 over ZL. Omega is 5,000, by the way, right? So you can find the value. So that's 1 over j 5,000 times 500 micro. Right, so you can get the numbers. I'm not gonna do the numbers here. So whatever the number is, that's in the Google Colab notes. They're all calculated. And y sub c is equal j omega c, right? So the total YEQ for the first one here, the YEQ, so this is the first one. So the YEQ is going to be equal 1 equal YR plus Y sub L plus Y sub C. Right? If you want to find the equivalent impedance Z sub EQ, just take the inverse of these. And then we try to find the currents. This currents here is, so let's see, we find the phasor first, as we did for the voltage division. So the I sub R would be equal to, so the I sub S we need to find first, right? So we haven't found this, we haven't found this one. I sub S should be equal to the amplitude of I sub S there, that's a 2. The phase angle should be negative 45 degrees minus 90 degrees. That's negative 135 degrees amps. And so the I sub R is equal to the Y sub R over YEQ, right, times the total current, I sub S. So the I sub S here is entering this node and the I sub R is leaving. So therefore we don't have a negative sign. So whatever the number you calculated, and then you convert that to the sinusoidal function. That should be equal to the magnitude of I sub R and times the cosine 5000 t and plus the phase angle of I sub R, whatever it is. That number already calculated in the Google Colab. And the same level we can find I sub L. Okay, I'm not going to repeat this. So I sub L is going to be Y sub L over YEQ times total IS. And you can find I sub R, I sub LT. And then the one for the capacitor current, I sub C is, look at this, the current I sub C is going into the nodes, right, entering the nodes, and I sub S also enters the nodes. So therefore, in this case, we need a negative sign there, and Y sub C over YEQ times I sub S. And whatever the number is, you can convert that to polar form, and then your I sub CT is going to be equal to the magnitude I sub C and times the cosine 5000 t and plus the phase angle of I sub C. Okay. So that's the simple example of the parallel connection. In the Google Colab notes, I cannot really bring that. So there's another one, the example number 3. That's the involved both the parallel and the series connection. Check that example out. And that's it for lecture number 3. See you next time. Remember, whatever you're doing, just keep going, never stop.